Good morning, friends. Last time we had Good morning, friends. Last time we were discussing the basics of graph theory. So we have defined what tree, co-tree, branches, twigs, etc. mean. Okay, in relation to network graphs. Now we will continue with this and we will find out the different relationships between the standard matrices. We also discussed about cut set. Now what are the cuts? I just forgot to mention last time. What is a proper cut and what is an improper cut? Suppose this is one graph of a network. I have chosen arbitrarily the orientation of different elements. These are the nodes. Maybe like this. You can have cuts along any chosen line. Okay, so these are the elements being cut. One may choose a cut like this also. That's also a cut. I can cut it with a scissor in any way I like. But if after a cut, when you are when you are separating the two parts of the entire network, then the parts must be connected to a node. All the cut parts, the cut branches must be connected to a node. There should not be a part like this. Then this is a proper cut. So this is a proper cut. You see, if I call these node numbers 1, 2, 3, 4 and 5, this is cut 1. By cut 1, these three elements are appearing like this. They are connected to node 1 and others are connected to node 2, 3, 4, 5. Is that all right? So node 2, this branch is cut into two parts. So one branch will be connected to node 1, the other part is connected to node 2. So node 2, node 5, node 3, node 4 and so on. These are the cut parts. So this is the line of cut. But if I consider this cut, you see this element will be hanging. It is connected to no nodes. Alright, it is an unconnected portion. So this is an improper cut. Alright. So when we consider cut sets, we will be considering only the proper cuts. So proper cuts will be cuts like cut 1 and cut 2 is improper cut. Okay. We also discussed about the network relationships that is established by the matrix A. AA was the overall matrix. We had the elements on this side 1, 2, 3, 4 and so on, and these are the nodes 1, 2, 3, 4, 5 etc. We have observed for each element there is a +1 symbol. We have assigned a +1 symbol when a particular element goes out from a node. So from node 1, if a particular element is going out, then node 1 will be assigned +1 sign, and wherever it enters, that will be given -1 sign. So say element number 1, this is element number 1, it will have a +1 sign here. Suppose this is node number 5, then it will be having a minus sign here. So like that, for all the elements there will be 1 plus 1 and 1 minus 1. An element can be connecting only, it can connect only 2 nodes, it cannot connect 3 nodes. So there will be only 2 non-zero elements, others will be all zeros. Now if you add up all the terms in a particular column, it will be 0, 1, plus 1 and minus 1, and rest are all 0. So if we consider any of the rows, it is not an independent one. Independent number of rows will be 1 less than the total number of nodes.
So this is not
You are having 5 rows. Say if you have a 5 node system like this, there can be many more nodes. Suppose we consider this 5 node system, and these are numbered, say 1, 2, 3, 4 like that. So each element will be connecting only 2 nodes. So there will be a plus 1 sign here, a minus 1 sign here. Okay. So this AA matrix, what will be its rank? What will be its rank? Can it be 5? Suppose there are 7 elements here. So it cannot be more than 5 by 5. Square matrix at the most can be of size 5 by 5. So the rank at the most could be 5. Now if you find that one of the any particular row is independent, it's not independent, means this can be generated with the help of the other 4 rows, then the rank will be less than 5, because its determinant will be 0. So it is not linearly independent. So we resort to a matrix A, taking one of the rows, any one of them as a reference, any of the nodes as reference, and deleting that particular row. Is that all right? So A will be known as the incidence matrix, whose dimension will be, suppose there are n plus 1 number of nodes. Okay, suppose n plus 1 is the number of nodes, then n will be the order of A, n by n, n by total number of branches, total number of elements. Say there are 7 elements, 7 by 4, that will be the dimension of A. Okay, E is the number of elements. So matrix A is having, say in this particular case, a dimension of 4 by 7 if there are 7 elements. So what will be the rank of A? It can be at the most 4. At the most 4. Let us see. The nature of matrix A. Now A I can partition. I can always select a particular tree. And arrange the elements of the tree first and then the links later. 1, 2, 3, 4, 5, 6, 7. I can choose a tree in such a way that the tree elements, say maybe 1, 2, 5, 6, 7. I can choose a tree of number, the element numbers 1, 2, 5, 6, 7. Then I'll put them first, and then the rest of the elements which we discussed last time are links that can be put separately. So a matrix A can be partitioned into AT and AL. AT refers to the tree elements, AL refers to the link elements. All right. So this is not unique, because the tree is not unique. Tree can be anything. I can choose any tree. There can be many possible trees. Okay. Now in a tree, for each column you have got, say these are the tree elements, you have got ones, at least one. You will get in matrix A, I have got AT, AL, this is n by n, this matrix is n by n, where what will be the number of elements in a tree if you are having n plus 1 as the number of nodes. If there are n plus 1 number of nodes, how many elements are there in a tree? One less? N. Only n. One less than number of nodes, is it not? So, if you are having the number of elements in a tree as n, then the tree matrix, that is AT, the submatrix, will have the order n by n. Okay? Is that all right? So, rest of the elements will be E minus n here. So, it will be n by E minus n. Okay. Number of elements can be anything. You can have large number of elements, highly interconnected network you can have. So, what will be the determinant of this A T? That will be determining the rank of the matrix, that is n. And what is this determinant AT? What will be the determinant AT? It consists of plus 1 and minus 1. Suppose we arrange the tree elements in such a way, this is node 1, 2, 3, 4. Okay. Suppose this is a tree. So, these are the links, possible links. There can be any more, many more connections. There can be a connection here also. Okay. Suppose this is a tree. These are the nodes given. I choose this as the reference. So, it will be 1, 2, 3 only. Suppose this is, 1, 2, 3, 4. This is 1, this is 2, this is 3, this is 4, and this is 5. These are the 5 nodes, and 1, 2, 3, 4, these are the nodes barring that reference one. Now, here you will find 1 to 4, both plus 1 and minus 1 will be included. Okay. 1 to 2 in this particular case, 1 to 2, again the second element will have plus 1 and minus 1. 2 to 5, 5, since 5 is eliminated, so there will be 1 plus 1. So, in the third element there can be a plus 1. I am not putting the zeros, rest are all zeros. Similarly, for 3, node 3, there will be 1 either plus 1 or minus 1. Okay, depends on the direction you choose. And for 4, again there is an element. So, for element, no sorry, these are the elements. So, 1, 2, 3, 4, there are 4 elements. Okay, these are the elements. Element 1, element 2, element 3, element 4. Okay. So, element 1, so all of them are having at least one element which is 1 non-zero element. There can be 2 non-zero elements also, 1 and minus 1, like this. For this element between 1 and 2, 1 and 4. So, this is having 2 non-zero elements, this is having 2 non-zero elements, others are having 1 non-zero element. Okay. If I take the determinant of this, say it will be 1 multiplied by the determinant of the 3 by 3 matrix. There, suppose I choose this one first, E1 first, which is a non-zero element. It can be +1 or -1. So corresponding to this, the determinant of AT will be ±1 into determinant of the element with one less order.
Yeah.
Okay, if I call it AT -1, basically that will be n minus 1 by n minus 1. In that again, if I choose the next element which is having a +1 in the second column, alright, so bring that first, then it will be again ±1 into AT minus 2, that will be equal to determinant AT minus 1. So like that, since there is always a non-zero element and they will be right up to the end, that means all the nodes are connected with some element or other. So you can choose always the nodes corresponding to their position, such that this will be always ±1 into ±1 into ±1 into, so the determinant will be always, the overall determinant will be always ±1. Do you get my point? What therefore we are trying to arrange is a matrix A such that we get all ±1s along this. It may be ±1, ±1, ±1 and so on. I have picked up nodes, alright, suppose this is node 1, this is element 1. I have picked up the nodes such that in the second position, whichever is having the second element as non-zero, I will place that as the second element here. Okay, I can either pick up the elements in that way, or I can change the order of the nodes, in such a way that 1, 1, 1, 1 they will appear like this. I can try to get a 0 here. Here there can be ±1s or zeros. This will give me a determinant which is 1. Okay. Now after partitioning A into these two submatrices AT and AL, we discussed about matrix B, that is the loop matrix. If you remember, you consider any tree first, then put one link at a time, then that will be called a fundamental loop. After the selection of a tree, you choose a particular link, so that is one fundamental loop. If the second loop comes, a second element comes here, then there can be a loop like this, but that will not be a fundamental loop, because fundamental loop is created out of a tree. There will be only one element at a time. There can be many loops, but all of them are not considered as fundamental loops. Fundamental loops means in a fundamental loop just one link will be present. This is one loop. Okay. If there is another element, alright, connecting these two nodes, then that will be another fundamental loop. But if there is a link here and there is another link here, that will be a loop, but that will not be a fundamental loop, because that is consisting of more than one links. So this is how we define the fundamental loop. So if you consider B with loops 1, 2, 3, 4, need not be always fundamental loop, any loop, and you are having the elements here, then what did we establish? A, if I multiply this, A transpose B, what does it mean? A transpose B, was it A transpose B?
0, AB transpose.
or AB transpose, either way you can take transpose of that also. Okay, AB transpose, we proved that it is equal to 0. Okay, what does it mean physically? Let us see. These are the elements here, these are the elements here, and these are the nodes. So the elements that will be connected here, these are the nodes, rest are all 0, and this 0 may not be, sorry, may not be. So you are having many of these, say node 1, 2, 3, 4 and so on. So each node will have a +1 sign and -1 sign somewhere connected, may or may not be there. And if I take B transpose, see A, matrix A will consist of +1 signs and -1 sign for any element. If that element is involved in a loop, then in the loop basically we are considering the loop like this. There are elements, how many links are present? One link at a time. Okay. So when you go along this from a particular node, there can be a large number of elements coming out, but in a loop only 2 elements will be coming into picture. Now one is going out, suppose this is going out, this is also going out, then in the loop this will have a positive sign, this will have a negative sign. So in the A matrix, though both of them are positive, in the loop matrix one is positive, the other one is negative. And other elements connected to matrix A will not be coming into picture in the corresponding elements in the B loop. Alright. So whenever we are multiplying A with B transpose, we are considering the elements B transpose means the elements connected in a particular loop involving that node. Alright. So only 2 elements will come into picture in a particular loop. There can be another loop considering this element and another third element connected to this node. Okay. So A B transpose is always 0 irrespective of the type of loop. We shall be considering only the fundamental loops. What is so big about fundamental loops?
Equations, loop equations.
If I consider B fundamental, means if we consider a tree, then what would be the elements of a tree and elements of the links in the B matrix? Can you partition B matrix into BT and BL? So let us see what BT and BL will look like. Okay. So B twigs, okay, twigs means the branch of a tree, and links, these are the loops 1, 2, 3 and so on. Now first loop in a fundamental loop matrix, in the first loop you are taking the first link, alright. The second link I am calling as second loop. So if I number the loops like that, then this will be 1, 1, 1 like that, is not. So that will be a unity matrix, an identity matrix. So for B fundamental, if I partition the matrix B into twigs and links, then the B link submatrix will be an identity matrix or a unity matrix. Is that all right? I hope this point is clear. For example, suppose I call this one as element number 1, the link number 1. Then this is a loop, is it not? This is a loop. I call that as loop number 1. So loop number 1, here we'll have 1 in the links. There can be anything here, I am not bothered. So far as this element is concerned, this is involved in this is included in this loop. Similarly, if I consider this as the second loop, second link, and this as the second loop, then this link is involved in this loop. So loop 2 will have element number 1 of this link. There cannot be any other element present in a loop, alright, because one link at a time is forming the loop. So in a fundamental loop, you will have a unity matrix here. If it is not a fundamental loop, then there can be many number of links. Okay. So BL is unity. Therefore, matrix BF is B twigs and a unity matrix. So what is AB transpose? Now B, this relationship is valid for any B. BF is only a class within B.
Unity matrix, identity matrix.
Which one? Unity matrix. Yes, it's the same thing. So ABFT is also 0. I can write A as AT, AL, partition it into two submatrices. BFT, if I take the transpose of this, okay, so AT BT transpose plus AL is equal to 0. Alright. So what is BT transpose? If I transfer it on this side, it is minus AL and AL, then AT inverse. Okay. So you can calculate BT. So from the A matrix itself, you can calculate B matrix, BF matrix. A matrix you partition, then take the transpose of the take the inverse of the submatrix AT, post multiply by AL, take the negative sign, so that gives you BT transpose. So the transpose of the whole thing will give you BT. Once you know BT, this you fill up with U, so that gives you B matrix. So loop matrix, fundamental loop matrix can be created out of the incidence matrix A. Now we shall go to what we discussed last time about an algorithm for generating any possible tree, generation of tree. As I told you, this is not a unique tree. Tree can be anything. There can be n number of possibilities. So this algorithm is also going to give you many possible trees. It all depends on how you handle the different operations and how you enter the data. So the first step is, normally we give the input as, say it is a resistance element. So we write R, then the starting node, say starting node can be 2, finishing node or ending node maybe 5, before this sometimes we give the element number, say it may be element number 7, this is the type, it may be resistance, inductance, capacitance, etc. So this is between node 2 and node 5, you have an element number 7. The data has to be entered like this, finishing node 5, and then element value resistance can be say 500, means 500 ohms. Okay. So the moment you define this, if it is L, it will be in Henry, if it is C, it will be in farads, and so on. So the units are decided by the type of element that you enter here. Anyway, after the data is entered, it will be only this 2, 5 and 7 which is of importance to us so far as the network graph is concerned, because we are not bothered how two nodes are connected, whether it is, they are connected by a resistance or an inductance or a resistance inductance combination. Okay.
What does 7 indicate?
In the network graph, it represents element number 7, because when you have given an orientation, an oriented graph means you give a particular orientation as well as a number to the element. You also number the nodes. From any network, when you draw the graph, you number the nodes and the elements, because finally you will be handling matrices, so the node number and the element numbers are relevant. In your matrix A and B, if you see the rows and columns, element number 1, 2, 3, 4, so number 7, element number 7, what is it which is connecting, say node number 2 and 3? Node number 2 and 3 may be connected by element number 4. Is it a resistance? Is it an inductance? So that must be specified in the while entering the data. Okay. So in the A matrix, initially we will be starting with all 0 elements. Okay. As and when the data comes, so we will start with element number 1, 2, 3, 4, whatever be the way of numbering them. After that, you sequentially go by the element number and their specifications. So element number 7, when it comes to 7, element number 7, it will fill up starting node 2, so 2 will be given a +1 sign, 5 will be given a -1 sign. So earlier they are all with 0, so 0 +1, 0 -1, so that will be modifying the matrix A. So this is how you keep on entering the data. Now after entering the data, what operations should we carry out? So there are 3 standard operations, we call them elementary operations, which are used here, which will be very subjective. When we choose the particular operation, it is not a unique one. One is interchange of 2 rows. You can interchange any 2 rows, say one with 3 or one with 4. I choose one with 4, you choose one with 3, so you will get 2 different transformed matrices. So matrix A is gradually transformed by various operations. One is interchange of rows. Next, you can change the signs. That means plus will be replaced by minus, minus will be plus. So change of sign. And then the third one is replacement of a row by addition, subtraction, all these and combinations of these operations of any other rows. Alright. So replacement of a row by the sum or difference of other rows. Replacement of rows of a row by sum or difference of other rows. Okay. Now, these three elementary operations we shall be using in transforming a matrix. Let us take up an example, then it will be clear what we are aiming at. Suppose we have but then one may ask, to what end? Finally, what is your aim? You keep on doing it. What is your aim? Our aim is to generate a matrix. Suppose these are the rows 1, 2, 3, 4, 5, 6, 7, and these are the nodes 1, 2, 3, 4. Okay. Now, we shall try to form a matrix form which is known as echelon form, which means there will be zeros, say it will be a step-like structure, Here we have ones, below this they are all 0, and the elements here can be A's, where A can be either 0 or 1. I am not bothered, 0, 1 or -1. Okay. It can be anything, but here to the left of this it is all 0. Then wherever these steps begin, these are the nodes which can form a possible tree. So here it is 1, 2, next one is 5, and then 6. You get my point? This is called an echelon form. So we are going to row echelon form. So we are going to identify those nodes where this 1 starts, okay, below which the elements will be all zeros.
This information is given a priori to us.
No, you have to create one, and then you will know what are the nodes to be selected for a possible tree. If you connect, what are the elements? 1, 2, 5, 6, they will form a possible tree. So since this is not unique, so somebody may get 1, 2, 3, 7, that also can be another possible tree then, element number 1, 2, 3, 7. So let us take up an example and see what results we get. Suppose you are given 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4. The values are 0, 0, 1, 0, -1, 0, 1, 0, -1, -1, 1, 0, 0, 0, 0, 0, 0. This is my A matrix. 0, 0, 0, -1, 0, -1, -1. Then fourth one is -1, 1, 0, 0, 0, 1, 0. Sorry. By the way, can you draw the graph? Can you draw the graph for this? So reference is the fifth, that is -1, +1. So let us see what the connection is like. So from the A matrix, can you redraw the graph? I am not using this space because I will be using for the conversion of matrix A. So I will just show you how the graph will look like. Okay. What will be the graph like? Element number 1 is connected between -4 and the fifth one. Suppose this is 5, this is 4. So this is element number 1. Okay. Element number 2 is between 2 and 4. So suppose this is 2 and 4. So from 4 it is going towards 2. Then 3 is between 1 and 2. Suppose this is 1. Then 3 is between 1 and 2. 1 is positive, 2 is negative. Okay. 4 is between 2 and 3. Suppose 3 is somewhere here. Okay, between 2 and 3. All right. This was element number 1. This was element number 2. Element number 3. This is element number 4. Okay. So from 2 it is positive, 3. This is node 3. Then element number 5 is between 1 and 5. So between 1 and 5, this is element number 5. Okay. 6 is between 3 and 4. So node 3 and 4. Is it all right? So this is 6. And 7 is between 1 and 3. So between 1 and 3, 1, 2, 3, this is element number 7. So this is the type of graph. Is that all right? So from a given matrix, you can always draw the graph. Now what is a possible tree for this? There can be many possible trees. So we are trying to identify one of them. I hope this is clear. Now what do you do? The first operation, I want a matrix as far as possible.
First one will be there.
If it is possible, yeah. All right, we will start with 1 there. So put 4, interchange row 4 with 1, and then change the sign of this. So next I will call it A1.
Sir, here only row transformations are allowed, or only we can column also transform?
No, you see elements, you cannot keep on changing both. Then what will be the location? So these are the nodes that we will be selecting. These are the elements that we will be selecting for the tree. So this will be retained 1, 2, 3, 4, etc. This side we have interchanged 4 with 1 and then change the sign. So it will be 1, -1, 0, 0, 0, -1, 0. Okay. Then 0. If you permit me, I will skip some steps. I will also change the sign of row 2 in one go. So it will be 0, 1, 1, -1, 0, 0, 0. Okay. Third one I will retain 0, 0, 0, -1, 0, -1, -1. And this one will be 0, 0, 1, 0, -1, 0, 1. Correct me if I am wrong. Is that all right? So I have already identified, you see, this is below this stair, it is 0. Now if I interchange these two, then this one will come here. So
You can change the sign of.
then a 2, if I interchange 3 and 4, this is 1, 2, 3, 4 new row numbers. So 3 and 4 if I interchange, then this will come here and 4 will go there. I mean this minus 1 will go there, okay, and then change the sign. So you will get 1, minus 1, 0, 0, 0, minus 1, 0, then 0, 1, 1, minus 1, 0, 0, 0, then we get 0, 0, 1, 0, minus 1, 0, 1, and then 0, 0, 0, 1. I have changed the sign, okay, I have changed the sign, so 0, 1, 1, 0, 1, 1. So element number 1, 2, 3, 4 may form a possible tree. This is a very simple case. In this particular example that we have taken, it came very easily. So 1, 2, 3, 4, let us see the graph here that we got. Element number 1, 2, 3, 4. Let us see the tree, how it looks like. This was 2, this was 4, this was 1, this is node 5, and then 3, this was 3. Now does it look like a tree? Five, 6, 7. This is element number 5. You see? So this is a possible tree. 1, 2, 3, 4, and 5, 6, 7. They form the links. Is it not? Another example we'll try. Suppose you are given matrix A, one, 2, 3, 4, 5, 6, 1, 1, 0, 0, 0, 0, then 0, minus 1, 0, minus 1, 0, minus 1. Then you have 0, 0, 1, 1, 0, 0, and then 1, 0, minus 1, 0, minus 1, 0. This is the matrix A. All of you can reconstruct the graph from the given matrix A. I told you just now how to make it. So A1, what could be a possible transformation of this? I can keep 1 there and then 2 here, second row, change the sign. Okay, so I'll get 1, 1, 0, 0, 0, 0, then 0, 1, 0, 1, 0, 1. Then third one is also possible, 0, 1, 1, 0, 0. Fourth one, if I subtract from here, then what do I get? 0,
Minus 1.
then
You are subtracting 1 from 4.
true,
So it will be 0 minus 1.
Okay. So how to eliminate that?
Multiply.
0 minus 1, I wanted to skip some steps so that I can write in a compact form here. So 0, if I subtract I get 0, if I subtract I get
Minus
1 or minus 1. I can subtract this one from here, so say plus 1. Then if I add with this second one, then that will create a 0. So subtract this from here, so row 1 minus row 2 plus row 1 minus row 4 plus row 2, what do you get? Let us be satisfied with that operation. Row 1 minus row 4 plus row 2, what do you get? This minus this, 0,
0 and
then this minus this plus this, so 0. So this minus this plus 1
plus 0 1.
plus 0 1, then this minus this and plus 1, so minus 1, then this minus this, so plus 1, this plus this minus 1. Okay. Now A2, yes. If I subtract from the third row, will that be all right? So up to first 3 I am not writing anything. It is only the last one which is of interest, which you want to modify. Okay. So 0 0, if I subtract from the third one, what do we get? 0 0 0, and add the fourth one, then what do we get? Then this one will come, so that will not be desirable. So if you subtract one from the other, I'll get a 0 here. Okay, I'll get 0 0 0, then I'll get 2 here. Then what will you do?
We can, but
Yes?
if others are 0 in that row, then we can divide it by 2, that row. In the row 4, if other element in that row 4 is 0, then we can divide it by 2, that row, 4 row.
Otherwise?
Otherwise, we have to multiply another row by 2 and then subtract it with the row 4.
Can you try that? Can you try that?
With
So this is a question, that means 1 2 3 4 will not be a possible tree, maybe 5 or 6. So the echelon structure will be like this. That means it will be again coming down at some other element. Okay, rest of the elements here will be plus 1 or minus 1. You have to tolerate that. That means here you are not in a position to get a 1 and below this all zeros at this point. It may come here, it can be 2 zeros, it can be 0 0 then 1. Do you get my point? So we'll take this in the next class, since it's already time. I deliberately took a very simple example first, so that 1 2 3 4 you can always arrange, but here it will be a stalemate. You cannot get 1 2 3 4 as the tree elements. Okay, thank you very much. Okay, good afternoon friends. We shall continue with our discussions on graph theory. Yesterday we had taken up a problem. The A matrix was given, please correct it, there is a minus sign here, I forgot to write that. 1 minus 1 0 0 0 0 0 minus 1 and so on. So we shall work it out here. So from A matrix, if you apply those transforms, what will be the possible next transform? I can change the sign of this, okay, I can change the sign of the second row. So this will become 1 minus 1 0 0 0 0, then 0 1 0 1 0 1, okay, then 0 0 1 1 0 0 1 0 minus 1 0 minus 1 0, okay. Then from here if I subtract this, this one was sign changed from the previous matrix. Then if I subtract row 1 from row 4, A2 row 1 is subtracted from row 4, we get 1 minus 1 0 0 0 0 0 1 0 1 0 1, then 0 0 1 1 0 0, then this minus this will give me 0, then 1, is that all right?
Yeah, 1.
Then
1.
minus 1 minus 1, then 0 0, sorry, minus 1 0, is that okay? 1 minus 1 0 minus 1 0, and then what do you do? This is having 1 here. So if I subtract this from this, 2 minus 4, row 2 minus row 4, what do you get? A3 1 minus 1 0 0 0 0, then 0 1 0 1 0 1, then 0 0 1 1 0 0, then 2 minus 4 will give me 0 0, next, yes please,